Welcome back to Summarize Science. Today, we're diving into a fascinating intersection of AI and quantum computing, looking at how one can solve the biggest problem of the other. Quantum computers are incredibly powerful, but they're also incredibly fragile and prone to errors from environmental noise. A key challenge is improving the reliability of quantum circuits, which is measured by something called process fidelity. Traditionally, attempts to improve this have been indirect, focusing on metrics like making the circuit shorter or using fewer operations. But these don't always guarantee the best reliability. This is where a new framework called FIDDLE comes in. Researchers at the University of Florida developed this novel approach to directly maximize the process fidelity. FIDDLE is a learning framework that cleverly uses two distinct AI modules to optimize quantum circuits. The first module is a surrogate model that acts like a highly efficient simulator. It learns to accurately predict the final fidelity of a quantum circuit, even with very limited training data. The second module uses reinforcement learning, an AI technique where an agent learns by trial and error, much like a person learning to play a video game. This reinforcement learning agent's goal is to find the best possible sequence of quantum gates. It gets a positive reward for selecting gates that are part of the main algorithm and a negative reward for adding extra gates that could introduce noise. When it completes a circuit, its ultimate reward is based on the final fidelity predicted by the first AI module. So, how well does it actually work? The researchers put FIDDLE to the test against several state-of-the-art methods, including the widely used Qiskit framework. They tested it on circuits for quantum optimization and quantum machine learning using several different models of quantum noise. These charts show the results for one of the test cases. The different colored bars represent FIDDLE and its competitors, including VIC, Qiskit, and another learning-based method called GNRL. Across every type of noise, from depolarized to a realistic real noise model, FIDDLE consistently produces circuits with the highest fidelity score. The performance gains are significant. In some cases, especially in more complex circuits and realistic noise environments, FIDDLE achieved fidelity improvements of over 10% compared to other advanced techniques. This demonstrates that directly optimizing for fidelity is a much more effective strategy. So let's recap the main takeaways. Quantum computers are held back by noise and unreliability. The FIDDLE framework uses a two-part AI to directly combat this. One part predicts circuit reliability, and the other uses reinforcement learning to find the most reliable design. The results show that this approach significantly outperforms current methods, creating more robust quantum circuits. What this means for the future is incredibly exciting. By tackling the critical challenge of reliability, technologies like FIDDLE help bridge the gap between today's noisy quantum devices and the fault-tolerant quantum computers of tomorrow. This work lays a crucial foundation for advancing quantum computing towards practical, real-world applications.